we go. So imagine, right? You see this right here, right? Imagine that we want to write this system. Let's see if I still remember it. Let's see if we can write the system in Wolfram Alpha, right? Right? In Wolfram Alpha, we're gonna write a matrix like that one. The entries that I gave you, right? And the way that we do this, yeah, it should work, is we're gonna put brackets. The first row. What was the first row over here? -1, 1, and 6. So -1, 1, and 6. So -1, 1. Let me put comma 1. Sorry. Comma 6. And that's the first row. Now we're going to move on to the second row. So to move on to the second row, we are going to put a semicolon like this. And what is the second row going to be? 3, -1. Yeah. So 3, 3, comma, -1, and 0. Let's see if this understands what I'm doing, right? Let's enter this. Oh, it's not understanding. Let me see if I can put, instead of comma, I put just nothing in there. Let's see what happens if this is like this. Yeah. Okay. Yeah, it didn't understand what I was trying to say. But anyway, so let's try this in Google, right? Google never fails. So matrix, and I'm gonna put RREF, right? Calculator. RREF is you put it in a matrix, and what it does, it will reduce it to the form that you want. And this form that we want, not the first form that usually you learn is called the RREF, the reduced row echelon form. And let's try to see if we can select. Let's see, it's a calculator, and let's do it here. The first one. So it says the number of rows. The number of rows in our system will be 2. Yeah, and the number of columns will be 3. And we submit this, and now let's input this. So the first row was -1, right? Then -1, 1. Yeah, -1, 1, 6. And the second one, what was it? 1. Yeah, sorry, 3. -1, 0. Thank you. 0. And what we do with this is we submit this, and let's see what this tells us. Look what it does. It tells you the operations. These are called EROs, the elementary raw operations, right? And what it does, it tells you that your matrix, the one that you started with, goes through a transformation, and it ends up with that last matrix over there. That's last matrix. This is what we call the RREF transformation of your matrix. And this is nice because think about this. What column was this guy here equal to? The X column, right? This was the Y column. And what this is telling you is the first line, it tells you that 1x plus 0y equals 3. So that means that x equals 3. This tells you that 0x plus 1y equals 9. So it tells you that y is equal to 9. So we get that x equals 3 and y is equal to 9 right away from it. You might say, but this is easier just to do it the other way, right? Yeah, because we have 2 variables. But if you have 3 variables, 4 variables, n variables, right, then this system will be preferable. And so we have to learn the mechanism behind this. Who started doing this? Jordan and Gauss. They came up with a system of inputting this in a machine, and the machine will just do these operations one at a time, and it will always give you an end result. When you are working in a factory, they have assembly lines, right? This line will be in charge of I don't know, taping a section, right? Then the next line will be so these are good for those assemble jobs. He will tell you how do you know that the packaging, the boxes will always be in one position at the end of the line. How do you know that? What if the box is sideways? What will the machine do to ensure that at the end the box is in the right position so that they can tape it, right? If you have a wooden factory, for example, right? It doesn't matter how the planks are coming. At the very end, every single plank has to have the same position, like the bottles, for example, as well, so that the machine can take it to the next assemble line, right? So this is a mechanism, right, that works for those type of systems. But for now, did we get the right answer? X equals 3 and y equals to 9? Yeah, we better have the same answer, right? And that's exactly what we have here, 3 and 9. Again, you want to express this as a system later on, because solving systems, we will have a technique of solving them, right? And the way that we write this out is the REF equals to 1, 0, 0, 1, and we have here 3/9. But I would say don't worry about this. This is for later on, and this is really nice for computer science. Computer science will go through understanding the mechanism of why, because this is an algorithm that goes through the first step, second step, third step, and so on. And you want to be able to express to a software how the mechanism will work, and the software will make it work, make it happen. But again, this is for much later, right, in the future. So let's take a look at another example. So suppose that a man has 14 coins in his pocket, all of which are dimes and quarters. If the total value of his change is $2.75, how many dimes and how many quarters does he have? A man has 14 coins in his pocket, and these coins consist of dimes and quarters. The total value in his pocket is $2.75. How many dimes and how many quarters does he have? So you can do this by a trial of error. Try to see what combination will be the right one. There's only one possible combination. The problem with doing this is that this works only if you have few, like, what if you have large quantities with many different types of coins? Then you will have to have a mechanism that will work, right, without fail. So let's see. The first equation will be this one right here. This is the number of coins that we have. The number of coins. Number of coins here. And the number of coins will be a total of 14. And these consist of quarters and dimes. So I'm going to say that X will represent the number of quarters, right? Can I use Q instead? Q for yeah. Okay, there we go. Q for quarters, number of quarters. And D for the number of dimes, right? And so the number of coins will be the number of quarters, Q, plus the number of dimes, D. This will equal to? 14th. This is the number of coins. The second one will be the total value. Total value. The worth of each quarter will be 25 cents. Right? 25 cents. So 25 cents per each quarter plus 10 cents per each dime will give you a total of 275. We express this in dollars, and then we discovered, hey, we have decimals. Let's just deal with cents, right, rather than dollars. So we were gonna have 0.25 times each quarter plus 0.10 times each dime will give you a total of, and you see how we have decimals there? Someone told me in the class, like, oh, I don't like big numbers. Can you put smaller numbers? So I put like numbers like this one, like decimals. Yeah. But anyways, let's can we multiply everything by 100, right? So that would be 25 Q plus 10D equals to 275. That's just a little bit better, right? It's a little bit easier than that. And we can even divide everything by 5, right? And if we divide everything by 5, we get. But anyways, these will be good enough. We have a system of equation. In the first equation here, can be solved for one of the variables there. Yeah. And if we solve for D or Q and then we plug it into the second one, that will be by the substitution method. Let's solve these by the addition method. So what variable do you want to cancel, the D's or the Q's?
The D's.
Let's cancel the D's, right? So on the first one you have 1D, or in the second one you have 10D. You want to have the opposite amount. So in the first one you multiply by negative 10. Yeah. So I'm going to write it like this. I have Q plus D equals 14th, and 25Q plus 10D equals to 275. I'm going to multiply the first equation by negative 10th. So I can have opposite amounts of these. I'm going to have this system of equation. Negative 10Q minus 10D equals to negative 140. And I have 25Q plus 10D equals to 275. I add them up. So we call this the addition method. Yeah, so I'm going to have 15Q plus 0D's equals to 135. There you go. And now all I have to do is divide everything by 15. So Q equals to 135 over, 15th. And 15 better go into 135. Yeah, otherwise we would be in trouble, right? Yeah, 15 times, what gives 135? Times 9th? Yeah, if you put times 10, that's going to be 150. And there's 15 less than that, so it's 9th, right? So this is 9th. Yeah. Yes? 9? Yeah. So, and so now we know that the number of quarters, right, is 9th. Number of quarters equals to 9. But what about the number of dimes? Yeah, so we know that Q plus D equals 14th. We know that you have 9 quarters, so you must have 5 dimes. Yeah, 5 dimes. And let's check this out, right? Because this is easier to check. If you have 9 quarters plus 5 dimes, 9 quarters, what is the worth of 9 quarters? That's like $2.25, right? Plus, and 5 dimes would be?
50 cents.
Yeah, 50 cents. Ouch. 0.50. Yeah. Do you guys agree that this will be $2.75? Mm-hmm. So it works. There won't be another combination of these things, right? There won't be. In combinatorics is a class for mathematics where we study the counting principles. What if you wanted to just get 275 by using quarters and dimes in different amounts? You don't have to have a specific amount of 14 coins. In how many ways can you possibly create $2.75 by using dimes and quarters? Yeah. How many? No, not infinite. How many? No. So in how many ways can you create an exact change of 275 with using just quarters and dimes, but not restricted to having 14 coins, but yeah, it is more difficult than that. And then we do this by counting principles. Yeah, so we learn some factorials in there, and it turns out that we try to connect things. Do you know polynomials, right? The answer for that is a polynomial. Yeah, which is really nice. Like how do we get these polynomials? It's really nice. So here is a system of equations, right? This is another example, right? And I'm not gonna give you the word problem. The word problems, you'll find them in the homework, right? But I will say just try your best to work on it on the final exam, and in our exam on Monday, I'm not going to put any word problems in it, right? But just know that in 195 you will see word problems in there, and you will see some rate problems, you will see some mixture problems, coin problems, number problems, and all kinds of problems in there. It's going to be 10.1 and 10.8. Yeah. So here is another example, right? So solve the system of equations and suppose that I give you something with fractions, just to put fractions in them, like 1/2 x minus y equals to 4, and say 3x plus 4y equals to 5. Let's put 5 here. It turns out that when we study systems, if you express them as matrices later on, like this one, it will be really easy to tell from the very beginning whether you have no solution or infinitely many solutions or one unique solution. And in mathematics, we have very nice words for that. When there is no solution, we say that the kernel of the system is just the empty set. Right? So a kernel is a really nice word that we use in mathematics for systems. We also have a word that describes the number. We call a word like a rank. The rank of a matrix. The rank will describe whether you have one unique solution or not. Okay, so do you think it's a good idea to cancel out the y variables in this case? Yeah. So we multiply the first equation by 4. You can, if you want, to eliminate the fraction first, if you want to, right? But it turns out that if you multiply the first equation by 4, yeah, that will just do the job, right? So here is what we have, right? So the new system that we will get will be 2x minus equals to, in the second equation, we leave it as it is, and what do? We just add them up, right? And what are we going to get? We're going to get 5x plus 0 equals to, 21. Sorry, 21. There you go. And what is x equal to? 21 over 5. And what is x? What is y equal to? Well, we can use any one of the original equations, right? So imagine that you use the first equation. Yeah. The first equation was this: 1/2 x minus y equals to 4. But we know that x here is 21 over 5 minus y equals to 4. So we have this 21 over 10th minus y is equal to 4. So yeah. So what I'm going to do now is you can do something like this if you want to. 21 over 10th minus 4 equals to y, right? Yeah, like that. And then you can multiply this 4 by 10 over 10, right? So what do you have?
Negative 19.
Mm-hmm.
Over 10.
Yeah, so negative 19th over 10th. But in this case, the solutions weren't so nice. But it's fine, right? So the solution, right, well, is x equal to 21 over 5, and y is equal to negative 19 over 10, like that. So, perfect. Now, let's take a look at the nonlinear case, right? 10.8. So in 10.8, we're talking about system of nonlinear equations. And this is a little bit more interesting because you can have more than one solution in your systems. So, system of nonlinear equations. It turns out that for this one, it's more convenient for us to use a substitution method. The substitution method. So here's our first example. So suppose that I have this one right here. Say x squared plus y is equal to 9th. And I also have that x minus y is equal to 3, negative 3, like this. So what makes this system nonlinear?
Got a square in it.
The linear systems, all of the variables have a power of 1, right? And in here, so I'm going to say solve the system of equations. Solve the system of equations. And in this case, this is a nonlinear system because of that. So if we add them up, right? So number one, if we were to add them up, addition method, we'll get something like this, right? So we have x squared plus y equals to 9th, and x minus y equals to negative 3. What variable will cancel out if we just add the systems up? The y's. So we will get x squared plus x equals to 6. So how do we solve this now?
Just a quadratic.
Yeah, so we move everything to the left side, and this will be x squared.
Minus 2.
So let's factor this out, right? Can we factor this out?
X plus 3.
Yeah, x plus 3 and x minus 2. If you couldn't factor this out, just use the quadratic formula, right? And so what are the values for x here? X is equal to?
Negative 3.
And the other one, x is equal to? 2. If x is equal to negative 3, then how do you know what y is? You use either the first or the second equation. I will use the second equation because it's linear. It's a little bit easier for me to play around. So using the second equation, I know that x minus y is equal to negative 3. But I know that x is equal to negative 3. So negative 3 minus y is equal to negative 3. What does that mean for y?
0.
Y is equal to 0. And so on the left side, we get this solution. We get the solution that x is equal to negative 3 and y is equal to 0. On the right side, if x is equal to 2, I have x minus y equals to negative 3. That means 2 minus y is equal to negative 3. That means that y is equal to?
5.
5. And we get this solution on the right side. The solution for this one will be x equals to 2 and y is equal to 5. But I'm describing the solution as a point, if you see it, right? As a point. What was the first equation representing? It was representing a parabola. Quadratic equation, right? And the second one is representing a straight line. If you intersect the parabola with a straight line, most likely they will intersect in twice. 2 points. So let's take a look at this in Desmos. I'll come back to this one, right? So in Desmos, right? Let's put Desmos. Let's enter these equations, right? The first one that I gave you was x squared plus y. Plus y is equal to 9th. And the second equation, right, is representing a different graph. So I'm going to represent this as a second graph as x minus y equals negative 3. Equals negative 3. There you go. So do you see where that they will intersect twice? You see it on the right side? Where will they intersect? They will intersect at these points right here. Easy. 2, 5, right? And it doesn't get big. 2, 5 and negative 3, 0. Are those the answers that we got? So the answers that we have are representing the intersections of this. Why will this be useful? Well, imagine in calculus you want to find the area bounded between the two of them. You better know where the first x, the intersection, the first x value where they first intersect, and the second x value where they second intersect, right? Intersect second time. So, but besides that, right? It's also good that if you think about it like this, imagine that you have a trajectory, the red trajectory, and the blue trajectory, and these are representing trajectories of two trains, for example. Then you will calculate this that in a way that no matter what happens, the blue train will never hit the red train. You might say, but they do intersect. Yeah, they do intersect. They might intersect at different times. So, for example, that will be a station, right? The red one would probably be at that station, say at 12 at noon, when the blue one will be at the same station but at different times. So we are going to add another additional variable, which is a parameter. That will be time, and time will determine when they will be at certain times. Not that they will be at 2,5, but it will tell you exactly the time where it will be at 2,5. So that's just think about adding another variable, another parameter onto it. So it's more precise on how things happen, right? Yes, there's going to be a point 2,5, but parameters will be able to tell you at what time this will occur. So there we go. So that's that. So here's another example, right? This is good? Yeah.
So did you solve for x or y or something?
Yeah, both. X and y. The solution will have x comma y. Mm-hmm. Is it good? Mm-hmm. Right. So here's another example, right? Let's see if we can manage to work with this. Imagine that you have x squared. So here, x squared minus y squared is equal to 7 over 2. And you have 2x squared plus 4y, and say this is equal to 13th, like this. So the way that we're going to do this is, let's do this by the addition method, right? So we have x squares here, and we have y there.
So can you go up for a second? So how you did x squared plus x equals 6?
So we just added the systems, right? So x squared plus x will be x squared plus x, and then y plus negative y, they will cancel out.
Or you could put x cubed, right?
No, that will be if you're multiplying them. But we're not multiplying them, we're adding them.
Plus y and negative y cancel out. So where did this x come from?
No, I just put it down.
Yeah. So
You cannot add.
so x squared plus x, right? What is that?
Or you just put it
Yeah, I just wrote it out here like x squared plus, because they're not like terms, we can't add them up, right? Yeah, the y and negative y, they just cancel out, but these ones didn't. Yeah. And on the right side, when we add 9 plus negative 3, that's just going to be 6. Yeah. Yeah. So looking at this system here, we can try to cancel out the x squares, right? If only we had, right, a negative 2 on the first line, right, then we can just add them up and they will cancel out. For the y's, can we cancel them out? And the answer, we can't cancel, because the first one has a y squared and the second one has a
Y.
so we shouldn't aim to cancel out the y variables. We should aim to cancel out the x variables. So I'll multiply the first equation by
-2.
-2. Not only do I want to have 2x squared, I want to have negative 2x squared. So when I add them up, they will cancel out. So I will get this system of equations, right? Negative 2x squared plus 2y squared equals to
7.
negative 7. Yeah. And the second one, well, it stays as 2x squared plus 4y equals to 13th. And now if I add them up, what would I get?
2y squared plus 4y.
Yeah. So the 2x, negative 2x squared and the 2x squares will cancel out, right? But I will get 2y squared plus 4y, equals to 6. And then I can move everything to the left side, or I can first divide by 2 if I want to. Yeah, and I'll get y squared plus 2y minus 3 equal to 0. And can I factor this out?
Positive 2 and negative.
Yeah, so if I couldn't factor this out, I'll just use a quadratic formula, and it will be the way to do it. So these will factor it out. Yeah, it will factor it out into y. What?
-1 plus 3.
Yeah, -1 and y plus 3. So now we're solving for the y variables first. So here we have y is equal to 1, and there we have y equals to. How do we figure out what x is? we can either use the first equation or the second equation, right? So let's use the second equation. It doesn't really matter. So we have this 2x squared plus 4y equals to 13th. So we know that 2x squared plus 4 times y is equal to 1 here, equals to 13th. So what do we know about 2x squared?
Equals to 9.
9th. And now we divide both sides by
2.
so we have x squared is equal to,
9 over 2.
and then we take the square root on both of that. We get plus and minus. So we have x is equal to
Plus and minus.
3 over the square root of 2. And you can rationalize it if you want to. So here are the solutions for the left side solutions. So x can be positive 3 over radical 2, but y will have to be 1. Or we can have negative 3 over radical 2, and y still has to be 1. So you can put them together if you want to. You can put plus and minus together in the same, right? And here is the second one that we have. If y is equal to negative 3, right, then we use 2x squared plus 4y equals to 13th. And we know that 2x squared plus 4 times negative 3 equals to 13th. We have 2x squared minus 12 equals to 13th. So 2x squared will equal to
25.
25. We divide both sides by 2 and we get x squared equals to 25 over 2. And x will be,
Plus or minus 5 over the square root of 2.
yeah, 5 over the square root of 2. And now these are another two possibilities here. Solutions. We have 5 over square root of 2, comma, negative,
5 over the square root.
right? And then the second one will be negative 5 over the square root of 2, comma, yeah, negative 3. So how many solutions do we have? 4. And what do you think these were representing from the very beginning?
Circle and a parabola.
Not a circle. If it was a plus, then it will be a circle.
2 parabolas.
Well, the first one,
Like hyperbola or something.
the name for that will be a hyperbola. And the second one will be a parabola.
Parabola.
Yeah. And you see how the first one has a minus in between, right? That will cause the hyperbola. And let's see how this will look like, right, in Desmos. So let's go to Desmos, and let's enter these ones now. So the first equation that I gave you, right? Yeah, let's see. Yeah, the first equation that I gave you was x squared minus y squared equals to 7 over 2, right? 7 divided by 2. And that's a hyperbola like that, right? And the next equation that I gave you was 2x squared plus 4y equals to 13, right? And that's a parabola like that, right? How many intersections will they share? 4. So here's one of them, here's another one, here's another one, and here's another one. And you can compute with the calculator that this will be about the points of intersection. The other one is more precise because you get the exact point, the exact numbers, right? You don't get an
Make it
approximation.
irrational numbers.
Huh?
I mean, you put like.
Rationalize them?
Yeah.
Yeah, you could rationalize them, but it doesn't help much, right? Yeah, but you can still find these intersections. Yeah, but these is good, but in an exam you can't just write these out. You don't have a calculator, first of all, and they want the exact number. What would that number be? Yeah. Question?
Going back to the work,
This one?
yeah, when you subtracted, you get rid of the 2x squared.
Mm-hmm.
How did you get the equation? Go up there.
So which equation?
When you subtracted, you get rid of the x.
From here?
Part, yeah.
Uh-huh. So I just added them up. So if you add the first one with the second one, these will add. They will just cancel out, right?
I see.
Yeah, because they have the same degree, right?
Oh,
Mhm.
so you did 2y squared plus 4y.
Mm-hmm.
So you did it.
Yeah. So here's another one, right? One last example. And then I will tell you a little bit about this weird guy, right, in India. So his name was Ramanujan Srinivasa, and he is a self-taught mathematician, and he's very brilliant. He saw things in his own way, and yeah. So his field in mathematics is number theory. So if you ever take mathematics and decide to go into number theory, they that's where you'll hear his name a lot. Yeah, he contributed to mathematics like a bunch. So here is another one. Say we have something like this. Say I want to solve the system where x. So here is the system. X minus y squared is equal to -3, and 2x squared plus y squared is equal to 4, like this. So what are we going to have here? Well, can we aim to cancel out the x's? We shouldn't, because they don't have the same degree, right?
Why is it cancel out already?
But the y's will be better, right? Not only will it be better, but they already have the opposite numbers, right, in there. So all we have to do is add them up. So we're going to have 2x squared plus x. The y's will cancel out. All of these will give you equal to 1. So 2x squared plus x minus 1 will equal to? Can we factor this out? Yeah. And again, if you have issues factoring things out, we went over how you factor it out by the AC method, right? So slowly, but you will get there. So what will this be? 2x and 2x, right? Sorry, x. Will x plus 1 work? A -1? That should work, right? Yeah. So what are the values for x? So x could be equal to 1/2, or x could be equal to -1. So we can use either the first equation or the second equation. It doesn't matter. So the first equation gave us, or we had x minus y squared equals to -3. But what do we know about x?
1/2.
Yeah, 1/2. So 1/2 minus y squared equals to -3. Right. And what does that mean? That y squared is equal to? Yeah, 1/2 plus 3. So it's like 3.5, so 7/2, right? So y squared is equal to 7/2. So what is y equal to then? Plus and minus, yeah, the square root of 7/2, like that. Nothing simplifies, right? And on the right side, so the solutions for this one, solutions. What would the solutions be? So x equals to 1/2, and y is equal to the positive square root of 7/2, and y is equal to x is equal to 1/2, and y is equal to the negative square root of 7/2, like that. What about the other option where x is equal to -1? So we have x minus y squared equals to -3. So we have -1 minus y squared equals to -3. So y squared will be -1 plus 3. So y squared is equal to 2. And y, therefore, it will be plus minus the square root of 2. And the solutions for this one, yeah. So these will be x is equal to -1, y is equal to the square root of 2, and x equals -1 and y equals square root of 2. Yeah. But these will be 4 solutions as well. So is it possible that we have 3 solutions in the system? And the answer is yes. It is possible. You might have a parabola and a circle like this, right? Like this. So this is a circle, and you might have a parabola that goes to a circle like this. So it is possible to have 3 points like this one, like that. You see, it is possible that the system gives you 4. It is possible that the system gives you no solution, right? Yeah.
Would it be possible if the system was undefined?
Like undefined, meaning that no solution? Yeah. So for example, if you are intersecting a parabola and a circle, and they just look like that, they would give you no solution. In that case, we write that solution is just empty, it has nothing in it. Yeah. So here is but in reality, every time you intersect two functions, you should always get solutions. But not all of these solutions are real numbers. Some of these solutions are complex numbers, right? So here is the last one, right? I'm going to graph this in Desmos. Ouch. Let's see, Desmos, and to see how it will look like, right? The first equation that I gave you, right, was x minus y squared equals to -3. The second equation that I gave you is 2x squared, plus y squared. Let me see. Plus y squared is equal to 4. And so here is what we have. It turns out that one of them wasn't a circle, it was an ellipse. And the second one is a parabola, but the parabola is not up or down, it's sideways, right? And here are the intersections of these ones right here. There we go. And you can see radical 2 is 1.4142, something like that, right? So that's good. And then the other one. You see that it happens in specific x values at x equals -1 at x equals 1/2, right? Just like we saw over there. Yeah. But that's good that we can do things like this. So here is this guy, Ramanujam Srinivasa, right? Let's just Google his name. Right? Ramanujam, yeah. Oh yeah, they did. Yeah. Yeah. Yeah, that's a book. Yeah. There's a book called The Man Who Knew Infinity. It's a boring book. Yeah. Srinivasa. Yeah, there we go. He's a self-taught mathematician, and he got into college, but he got kicked out of college because of his English examinations and languages and writing examinations. But he's great mathematician, and he in the book The Man Who Knew Infinity, he gives this system of equation to a friend of him. Like he says, can you solve this system? And he gives him this: the square root of x plus y equal to 7th, and x plus the square root of y, something like that, right? Let's see. Yeah, I think it's 11th. Yeah, 11. There we go. So the book, this is in the book The Man Who Knew Infinity, right? He gives this, and the story goes that he's in school, and a boy sits next to him and says, "You can't be my friend." He said, "Why not?" He says, "Oh, I only hang out with people of my caliber," and he says, "Oh well, I'm smart," and he gives him this problem to solve, and the kid stares at it and gives him the solution, right? And then Ramanujam says, "Oh, you're smart. You're like me too." Yeah. So anyway, it turns out that systems like this one right here, when this system, for example, it will be very complicated if you were to try to solve it by hand, because then you solve for x, substitute in the other one, and you get a 4th degree, right, answer. But you can just test it out, and to see what numbers will work into it. And if you test it out, what numbers do you see will work into it?
Like negative numbers can't work.
Yeah, negative numbers can't work because you have to be able to take the square root of x and the square root of y, right? But what will be
9
those
and
solutions?
4.
9 and 4. Yeah. So it turns out that it doesn't matter. Yeah. X equals 9, y is equal to 4. That works. And if you do x equals 4 and y equals 9, will also work, right? And you can think of two possible solutions for a system like this. Then for matrices we'll have to talk about non-linear systems. Matrices are very, very nice for linear systems. For non-linears, there's a lot that you can do there. But what we do in matrices, just like we do in functions later on, we expand them as series, power series. And so imagine that you have a polynomial and you start smoothing it out by approximating this polynomial with simpler functions. Like sine, for example. Sine is just nothing more than a polynomial that just wiggles back and forth, right? So that's what we do. We started replacing sine with what we call a power series. So sine of x starts looking like this. Sine of x is approximately equal to x. If x is really small. You've seen this before, right? hopefully, right?
X is 4 and Y is 9 doesn't work.
X equals 4. Yeah, probably one of them doesn't work, right? You sure?
On the
Yeah,
bottom.
It does work, right?
It does work.
Because the variables, you can interchange them. Very simple.
No, but 4 plus 3 is not 11.
Doesn't work on either.
Yeah, because if you get like the square root of 4, it will be plus, and you will be positive and negative 2.
2 plus
Uh-huh.
9 is
So it
not
will be
7.
negative 2
So,
plus 9.
does it work? The first one works?
I think you gotta switch them, right?
2 plus 9.
Oh, so if I switch them, that will work?
I think you work like that.
I think
Like,
it works.
There's only one solution.
2
the
plus.
first one is
It's just 9, 4.
It's just 9 and 4.
X equals 9, Y equals
Because the square root of 4 is also negative 2.
Yeah.
It's 9. It's
yeah.
So which solution works? The first one or the second
first
one?
side.
4.
First one works,
Mhm.
but the second one doesn't? Okay, I believe you. Okay, yeah, okay, great. There we go. So continue with the sine of x is approximately x if x is really small, if you're really, really close to it. But what if you're not so close to it? So we add or subtract this guy here, x to the third divided by 6. And then this is better, not only for small angles, right, or values for x. You can test it out for a little larger. But then you can even add a little bit more to this. You can even add x to the fifth divided by 120, like this. And the more you add, the better approximation. Well, how do you know what to add to get better approximations on it? But that's what Taylor spent his life on, right? Taylor series and Maclaurin series. This is like, how do you replace functions with polynomials, like e to the x, for example, exponentials, sine of x, cosine of x, inverse functions, right? And anyway, so this is a very nice topic to study in calculus. After calculus, you start learning how to do this, and you need derivatives for all of this. So that's why calculus is applicable for it.
Are there like any mathematicians in this century that have their how you talk about all these men
Mhm.
having all their ideas in textbooks and stuff?
Uh-huh.
Are there anyone in this century that has?
Yeah. So this professor in UCLA, right? UCLA. His name is Terence Tao, right? Terence Tao, and he's like very young. He teaches at UCLA University, and he's brilliant, right? But his field in mathematics is number theory as well. But you can see that he's very young, and I think when he turned 20 something, he already had some of the best. So when he was a child, he was a prodigy, right? He was like very popular for being a wizard in mathematics, and but he teaches at the UCLA University. I think he has come here, but just to visit, not to give a talk or anything like that. Yeah. By the way, you guys someone asked me here if I ever met Michikaku, right?
Yeah.
When you guys went to the library, right?
Yeah,
The
that was
tour.
him?
He was coming out of the library.
Wow, he was so sweet.
Yeah, you guys didn't see him? Yeah, that's him. Yeah, so you see a lot of people around, and they look like ordinary people.